Okay, so number 53, the gravitational attraction between two objects with masses m1 and m2 separated by a distance x is F is equal to g times m1 times m2 all divided by x squared, where g is the gravitational constant. A, how much work is done by gravity with the separation changes from x1 to x2, assuming x2 is less than x1? And B, if one mass is much greater than the other, the larger mass stays essentially at rest while the other mass moves towards it. Suppose a 1.5 times 10 to the 13 kilogram comet is passing the orbit of Mars, heading straight for the sun at a speed of 3.5 times 10 to the 4 meters per second. What will its speed be when it crosses the orbit of Mercury? Astronomical data are given in the tables in the back of the book, and the gravitational constant for this position in space is equal to 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. So that's a lot different than how it is on Earth, which makes sense, obviously, but it's so crazy how different that is. So for A, we're just trying to find a formula for what the work is. It's going to be in terms of G, M1, M2, X, and X2. And so we know that we have this for force here, and it's going to be from X1 to X2. And we know that the force changes with the change in position of X. So we need to integrate, and the integration is a little bit tricky, but it's not too bad. So work is equal to the integration of force times dx, which is going to be equal to, just bringing this guy down here, dx, which is going to be equal to gravitational constant times m1 times m2 divided by x. And that's because when we are dividing by x squared, that essentially means we're multiplying by x to the negative 2. And for integration, we add 1. So we're going to get x to the negative 1, and then we multiply by that new exponent, but since it's on the bottom, the negative 1 goes away essentially, so we don't have to multiply by a negative 1. So, and we're going to take that from x1 to x2. And so we get this for work, and this is our formula for work, and this is essentially what this situation looks like. We're going from this distance with these two masses to this distance with the same masses, but I didn't write it to the same scale. Now for B, it's a little complicated because we have all these things, and I have all the measurements here so you guys don't have to look it up. This is all the information you're going to need for this section. So essentially we have a comet that is rushing towards the sun, and it just so happens to pass the orbit of Mars as well as the orbit of Mercury. And we're assuming it's passing right on the outside of it because we're given the full orbit of these two here. And of course, this is also not to scale. So we can't use anything with constant acceleration because the acceleration isn't constant at all. As we're going through these two orbits, it's just going to completely change. And we also know that the velocity changes, and so there has to be some form of acceleration change. And so we know that the total work is equal to the change in kinetic energy, and we know that the change in kinetic energy is equal to the change of 1/2 the mass times the velocity squared. And so we're going to use our work equation, or at least half of it, from up here, and we're going to equate that with the change in kinetic energy. And we're going to do that twice because we have two different values of x. We have x1 and we have x2. And we have m1, m2, m1, v initial squared, and v final squared. We're going to be solving for v final squared. And so it looks a lot like this here. And it's a little messy, but it's not too bad actually once you put in all the numbers. So we have the Mars's orbit section here, and we have the Mercury's orbit here. And it turns out that the mass of the comet cancels out during the calculations, and I'm not going to show you because it takes a long time to rearrange all of this. So please just trust me on that one. It does cancel out, I promise. And so basically our calculation with all of the numbers plugged in is going to look a lot like this, and we're basically going to solve for v final here. And I'm not going to rearrange this for v final for you. So it turns out that V final is equal to 6.82 times 10 to the 4th meters per second. And does this make sense? Well, our initial velocity was 3.5 and it increased to 6.82. So it does make sense because the closer you get to the sun, the greater the gravitational pull of the sun. So, yay, we found the answer. And so our learning goals for this problem was work and kinetic energy relations. We really needed to know the way that work deals with kinetic energy and how kinetic energy works with mass and velocity and all these other things. And so we really needed to know how to work around these two parts of force. Thank you very much. I hope you have a lovely day and a safe and healthy holiday season.